Greetings, I'm Ivan Peng, professor at National University of Singapore in Economics and Strategy and Policy. This is a brief review of econometrics. In this brief review, I shall first cover hypothesis testing, then go on to discuss ordinary least squares, which is the most common method of estimation, and then finally present to you discussion of causal inference. What exactly can we conclude from data using econometric methods? First, hypothesis testing. All empirical analysis begins from a set of theoretical analyses from which we develop a hypothesis, or perhaps multiple hypotheses. The hypothesis that we want to test or prove is formally called an alternative hypothesis, usually denoted as H subscript 1. To accept the alternative hypothesis based on the data, we have to reject the null hypothesis, normally denoted H subscript 0. If the theoretical proposition is true, is valid, then the data should support the rejection of the null hypothesis in favor of the alternative hypothesis. The strategy of econometrics is to set up the data and the estimation so as to test and possibly reject this null hypothesis. Based on the theory, we set up an estimation model, which is a formal description of the relationship between the explanatory variable, what we think affects some outcome, and the outcome. And in this formal model, we denote the explanatory variable by X and the outcome by Y. Later on, we shall discuss how it helps to make the X larger in the sense of adding control variables to the explanatory variables. So in this case, the outcome will be explained by the explanatory variable, which is the one of central interest for theoretical grounds, as well as control variables, which help to improve the precision of the estimation. The Y, the outcome, in a statistical or econometric sense, we also call the dependent variable, because if you refer to the equation, Y, the dependent variable, is a function of a constant, beta subscript 0, plus a coefficient, beta subscript 1, multiplied by the explanatory variable, or in the more general case, beta 1 might be a vector of coefficients multiplied by the explanatory variables and the control variables, plus a final term U, which represents the error, because we do not expect a perfect statistical fit. There will always be some random variation. U, the error, is the difference between the actual Y, the actual outcome or dependent variable, and the true model. So this is Y, this is the true model, beta subscript 0 plus beta subscript 1 times X. Y minus beta subscript 0 minus beta subscript 1 times X is U, which is the error. And to reiterate, the focus of the empirical estimation will be on beta subscript 1, the coefficient that will tell us whether the null hypothesis can be rejected or not. Before plunging into running regressions, it's always good to first examine the data. Statistical economic net trick papers usually begin with one table entitled Summary Statistics. Look at the summary statistics for the dependent variable, the explanatory variable, and the control variables. What are the means? What are the standard deviations? Especially look for outliers. Graph the data. So here I've shown you a graph of the effect of a new scan-only checkout system in a supermarket relative to the cashier's scanning speed in the conventional checkout method where the cashier both did scanning and collected payments. And you can see that generally there's a negative relationship. If the cashier was faster in scanning at the conventional checkout, the new technology increased their product scanning speed relatively less. And here, this seems to be an outlier. There's one cashier who is very slow in the conventional checkout and then increased hugely her speed when switching to the new technology. So graphing the data is a good way of identifying outliers, like this one, and to a lesser extent, this one. You can also look for outliers just by studying the means and standard deviations. If you see an observation with whose value is of the variable, the outcome variable is say 4, 5, 6, 7 times the bigger than the mean, 4, 5, 6, 7 times standard deviations bigger than the mean, then you might think that's an outlier. That might be an observation that you want to drop from the analysis. Having defined the model, examined the data, the next step in the hypothesis testing is to decide whether to set up the test of the null hypothesis as a one-tailed test or a two-tailed test. Referring to this figure, which shows a two-tailed test, we reject the null hypothesis if the error terms are sufficiently large. So either here, sufficiently in the negative region, or sufficiently in the positive region, where we are assuming that the null hypothesis is that the coefficient beta 1 is 0. So these two regions add up to what we call the significance level, the probability of rejecting the null hypothesis when it's actually correct. If we set up as a one-tail test, let's say we reject if the coefficient beta 1 is negative, then all the error terms, the 2.5, will be clustered here. And you can see that will be a larger error, and there will be no error terms on this side. And this, we can also do the same for different levels of significance. I've just illustrated for the 95% confidence interval, we could go for a 99% confidence interval, in which case the area of rejection will be smaller. It will be only 1% here and 1% here in a two-tailed test. Or we could estimate with a 90% confidence level, in which case the rejection errors would be larger. The areas of rejection of the null hypothesis would be larger. There'll be 5% on this tail and 5% on the next tail. In choosing between the one-tail test and the two-tail test, consider that typically the prior research, whether it's empirical or theoretical, will point to some hypothesis, the direction of that coefficient beta 1. It might be positive or it might be negative. So it might seem logical to carry out a one-tail test. However, a one-tail test, as you saw from the previous figure, allows a bigger error region. So it's less conservative than a two-tailed test. In choosing between one-tailed test, two-tailed test, one option might be to use the one-tailed test, but with a higher confidence interval, let's say 99% instead of 95%. that is a lower level of significance. The challenge with the one-tailed test is what if the data shows a result in the wrong direction, where we think that our hypothesis is that beta 1 is equal to 0, is greater than 0, but the data points to beta 1 being less than 0. So generally the convention seems to be to apply a two-tailed test, and the conventional levels of the confidence intervals, the 95% and to be more stringent, the 99% levels. In the next segment, I will present the most common and basic method of estimation in econometrics, the ordinary least squares regression, commonly abbreviated as OLS. OLS fits a linear regression model where X, the explanatory variable, explains or predicts the outcome or the dependent variable Y. Actually, in an earlier slide, I wrote down the equation for an OLS model. Y equals beta subscript 0 plus beta subscript 1 times X plus U. Recall that U in that equation was the error term. Referring to this figure, this could be the Y variable, this is the X variable, and the dots mark the points, each of which is an observation of Y and X. For instance, this is the observation, one observation where X is around 20 and Y is about 110. This is another observation where X is about 85 and Y is 320. Plotting all of these points, ordinary least squares plots a linear relationship called the regression line between the Y and the X. Now, there are many possible lines that one could draw. OLS chooses the line which minimizes the sum of the squared residuals. The residual is the difference between the Y and the estimated model. So here's a Y, and there's the estimated model. For that X, that's the residual. Residuals can be negative, they can be positive. Now, the reason why OLS is set up to minimize the sum of the squared residuals is to give equal weight to positive residuals and negative residuals. They're treated equally, and to give relatively more weight to residuals which are relatively far away. So it's the squared residuals. This residual here is a small distance. The square will be much smaller than this residual, which is positive but larger. The square will be extremely, much larger. We measure the fit of the OLS regression by a statistic called the R-squared, which is the degree to which the model, this linear regression model, accounts for the distribution of these scatter points. The R-squared can be adjusted for the number of explanatory variables. That's called the adjusted R-squared. The R-squared is the statistic with which we measure the fit of the model, how well it explains the data. The next statistic that's important in hypothesis testing is the degree of statistical significance of the estimate of the parameter of interest. Think of a regression model that we put down earlier. Y equals beta subscript 0 plus beta subscript 1 times X plus U. And let's consider a test of the hypothesis two-tailed with a null hypothesis that beta subscript 1 is 0. We need to understand the precision of the estimate. How likely is it that when we say that we reject the null hypothesis, that we're not falsely rejecting the null hypothesis? And this we gauge by two fundamental or basic estimates. One is the size of the parameter estimate, how large is the estimated value of beta subscript 1, and how dispersed the possible estimates of beta subscript 1. So one is the mean and the other is the standard error. And from them we compute a statistic called the p-value. The p-value is motivated by asking, if the null hypothesis is true, what is the likelihood of obtaining an estimate that is equal or more extreme than observed? So this is what is the likelihood of us making a mistake, falsely rejecting the null hypothesis. The smaller the p-value, and if you refer to that graph which I showed a few slides ago, the smaller the p-value, the more extreme the deviations have to be from the null before we reject the null hypothesis. So if we went for 1% rejection, that is 0.5% in each of the tails, that would be a much more conservative test rejection than if we ask for 2.5% in each of the tails. We reject the null hypothesis if the p-value is below some level of significance. The conventional levels are denoted alpha, 10%, 5%, and 1%. 10% being the most lenient and 1% being the most stringent. A way to think about the conventional significance level, say alpha of 5%, is that in 1 out of 20 IID, that is independently and identically distributed trials, we would get a false positive, even if that is, we would reject the null hypothesis, even if the true effect is 0. That is, we would wrongly reject the null hypothesis. Now, it's impossible to never wrongly reject the null hypothesis. Well, the only way to do so would be to never reject it. So we'll never find evidence in favor of the hypothesis. So it's always a matter of choosing an alpha which we're comfortable with. Now, let me stress that we may find that a beta subscript 1 is statistically significant in the sense that we can reject the null hypothesis that beta subscript 1 is 0 with, say, an alpha of 5%. That is statistical significance. A completely separate matter is economic significance. That is, it could be that our X affects the Y statistically significantly, but it's not economically meaningful. And to appreciate the economic meaning, one way is to say, what if that X variable were to increase by 1 standard deviation? What would be the effect on the Y? Would it be of the same order of magnitude change in the Y? If we find that a 1 standard deviation change in the X causes, say, a 0.0001 change in the Y by 0.001 of the standard deviation of Y, that's probably not very economically meaningful. So it's very important to understand the difference between statistical significance and economic significance. In presenting the previous slide, I referred to a statistic to measure the precision of the estimate. And that statistic derives from the standard error of the estimate and the estimate itself. So that statistic is called the t-statistic, which is defined as the estimated coefficient divided by its standard error. So referring to this table here, where the mileage of cars is regressed on the weight, length, car type, and a constant, we see that the coefficient in that regression, the coefficient of weight is minus 0.00385, and in parentheses is the standard error, 0.00199. To compute the t-statistic, we would divide minus 0.00385 by 0.00199. That is the t-statistic. Theoretically, the t-statistic converges to the standardized normal distribution. That is, with a large enough sample, the t-statistic follows the distribution of the normal. And we can compute the p-value of any estimate as the probability that the t in a two-tailed test, the probability that the t that we observe is either bigger than the standardized normal or smaller than the standardized normal. Using the normal distribution for two-tailed tests with a large enough sample, for the confidence significance levels of 10%, 5%, and 1%, the critical values of the t-statistics are 1.645, 1.96, and 2.575. So this means if we find a t-statistic that is bigger than 1.96, we can say we reject the null hypothesis at a p-value of 5%. Conventionally, economists report statistics with stars. So one asterisk represents a p-value of less than 10%. Two asterisks represent a p-value of less than 5%, and three asterisks represent a p-value of less than 1%. Ordinary least squares estimation is founded on four key assumptions. The first is that the model is linear, as we assumed, as I illustrated in a previous slide. So an increase in x increases y by beta 1 times that increase in x. That's the meaning of a linear model. And if you draw a scatter plot where there's just one variable in x, then you see the regression is represented by a straight line. The second assumption in underlying ordinary least squares is that there's no perfect multicollinearity, which means that if there are multiple variables in the x, that is, we have more than one explanatory variable, or we have an explanatory variable and some control variables, they're not actually the same. They don't move completely together. If they completely move together, which is statistically called multicollinearity, then it won't be possible to estimate the ordinary least squares. The third condition is that there are few large outliers. And the technical condition is that the fourth moment of the relationship must be finite. And most importantly, the two conditions on the error terms. One is that they are independently and identically distributed, which is abbreviated IID. A counterexample would be where some observations are duplicated. That would not satisfy the IID condition. And the second condition on the errors is that the expectation of the error conditional on the explanatory and control variables is 0. Formally, that's written as E, expectation operator of U conditional on X is equal to 0. And this is the main worry that we will have and discuss in the next segment on causal inference. Having reviewed the concept of hypothesis testing and then introduced the method of ordinary least squares, the final topic in the review of econometric methods is the concept of causal inference, which is what can we conclude from the data and estimates. Let me present the concept of causal inference first in the case of a continuous explanatory variable, and narrow down to the case of a single continuous explanatory variable. The regression coefficient of the estimated of beta subscript 1 will depend on the covariance between y and x, the covariance between the dependent variable and the explanatory variable. In the case of the linear regression, we can substitute for y beta subscript 1 plus beta subscript 0 plus beta subscript 1 times x plus u, the error term, the covariance of that with x. And using algebra, we can simplify that to be the sum of the covariance of beta subscript 1 times x with x plus the covariance of u with x, and which further simplifies to beta subscript 1 times the variance of x plus the covariance of u with x. Ideally, we want the covariance of u and x to be 0. Then we can use that equation, reshuffle, and we get an estimate of beta subscript 1 as the covariance of y with x divided by the variance of x. But what if the expected value of the error conditional x is not equal to 0? Then the covariance of u with x is not equal to 0, and the covariance of y with x is not equal to beta subscript 1 times the variance of x. And we say that the relationship between x and y is confounded. What might cause the confound? Or equivalently, what might be the sources of biases that cause the expectation of u conditional on x to be not 0? And the OLS estimated to be biased. Here are 3. One is a possibly omitted variable, and which might give rise to some selection bias. So an example, if you think back to the quote from Tolstoy, he noticed that when the oak buds open, cold winds blew. And he challenged the view that it was the oak buds blooming that caused the cold spring winds. Well, clearly, there is a third omitted variable, namely spring weather, the onset of spring that causes both the buds to bloom and the spring winds. So that's a very simple example. Let me give you 2 more examples from a productivity innovation context. Suppose that we find a relationship that foreign-owned businesses are more profitable. Does that mean that foreign ownership implies higher profit? It could well be that this omitted variable of management quality. Foreign-owned businesses are better managed, and that's why they're more profitable, not because of their foreign ownership as such. A third example, it might be said that businesses which adopt new technology are more productive. Can we conclude that there's a causal relationship from new technology to productivity? Perhaps not. It could be that those businesses also have workers who are more skilled, and the businesses with more skilled workers also adopt new technology. So we cannot draw a causal line from the adoption of the new technology to productivity. A second source of bias or confound is simultaneity in the relationship between the y variable and the x variable. So we think of the y variable as the dependent variable and the x variable as the explanatory variable. But what if we switch their roles and say that the y variable is the explanatory variable and the x variable is the dependent variable? This is very commonly called reverse causation. A couple of examples. Startups with patents are more likely to have VC funding. So here we think of the causal relationship being the startups with funding, patents, being able to attract VC funding. But it could well be that the startups that get VC funding have more resources with which to apply for patents. So if we had just drawn a correlation between startups with patents and VC funding, that can be explained in both directions. A third source of confound or bias is measurement error, which is non-classical. The classical measurement error is where when we measure y or x, and the errors in the measurement, they're not correlated with the y. Those don't pose any problem, and they cause the estimates of the beta subscript 1 to be attenuated. So we are over likely to reject the null hypothesis. However, if the measurement error is not classical, that is, it's correlated with y, then the outcome of the estimation will be biased. The example is estimation of total factor productivity, where the measure of the output, which is the dependent variable, might be systematically related to the inputs through, for instance, market power of the producer. One possible way to help resolve the issue of confound, that is the expectation of u conditional x is not equal to 0, is to add control variables to x. So we had thought in first discussion we posed x as being one explanatory variable, but it could be expanded to include additional control variables. And it could well be that if we choose the right control variables, we could, for instance, be able to resolve omitted variable bias. If we go back to the Tolstoy example, if we controlled for the spring, onset of spring, then we would be able to avoid any the confound. And then we would have the expectation of u conditional x equal to 0. How do we choose the control variables? Two things to consider. We want to leave enough variation in the y and x to be able to estimate the beta subscript 1. So we want to avoid over-controlling. Another thing to bear in mind is that the interpretation of the estimate of beta subscript 1 will depend on the control variables that we include. For instance, if we're thinking of the effect of the change in law, law, such as patent law, on patenting, we could estimate this two ways. One with control for R&D expenditure, and the other without control for R&D expenditure. Then the coefficient of the law would have two different interpretations. In one, it's the full effect of the change in law on patenting, and the other is the effect of the change in law holding constant R&D, which are two different interpretations. And the one will show, by comparing the two estimates, we'll be able to see the indirect effect of the change in law on patenting through changes in R&D expenditure. Besides adding control variables suitably selected, an alternative approach or a complementary approach is to design the experiment in a quasi-experimental way. This means identifying a control group that is an appropriate counterfactual under the specific conditions. And having identified a control group, the variation in the treatment variable is quasi-random or as good as random. Three popular designs for such quasi-experimental. One is the regression discontinuity, or it's related, the regression kink design. The second is difference in differences, and the third is instrumental variables. In the main lecture, I motivated regression discontinuity. Let's see a couple of examples next. Abrams and Wagner, in their 2013 paper, carried out a study of a change in Canadian law from a first to invent to a first to file patent system. First to invent meant that the first person to invent a technology could get the patent, regardless of when they filed, whereas first to file meant whoever was first to file the patent application would get the patent even if they were not the first to invent the technology. They drew the following plots to compare the proportion of individual inventors amongst all inventors, the others being organizational inventors, people employed by companies or universities or research institutes. In the US, which was the top series, the solid round circles, with the Canadians, the hollow diamonds, around January the 1st, 1990, which is when the new Canadian law came into effect. You see that around January 1990, amongst US inventors, there was no change in the proportion of individual inventors. But in Canada, around that month, there was a discrete drop of about 0.2, that is 2%, or something like almost 1 out of 5 drop in the proportion of individual inventors. And this suggests that the change in law had an effect in discouraging individual inventors because they didn't have the same resources as organizational inventors to be the first to file. The usual etiquette, as illustrated by the Abrams and Wagner paper, in regression discontinuity design studies is to graph two plots. One plot is in the outcome of interest to show that there's a discontinuity around that cutoff. That cutoff could be a date, as in the Abrams and Wagner study, or it could be some other variable along which there's a discontinuity. For instance, some famous studies were done on constituencies and the degree to which they supported the Republican or Democratic Party. And round about the 50% mark, where a seat swings from one party to the other, is a discontinuity. The other kind of plot to show in a regression discontinuity study is to do a falsification, to show that there's no discontinuity in other variables that possibly affect the outcome. So for instance, in the Abrams-Wagner study, it would be good to show that there was no shift in R&D around January 1990, or no shift in any other variable that would affect the participation of individual inventors in patenting. The second quasi-experimental design is difference in differences. And this we can apply in a situation where the treatment is administered according to some criteria which are not related to the outcome of interest. Then the population can be divided into two groups: a treatment group, which receives the policy or business strategy, and a control group which does not receive the policy or business strategy, and the control group provides a counterfactual. Typically, difference in differences is a method which we apply to policies or strategies that are implemented at some time. So dividing the time between a before period when the policy or strategy was not in effect and an after period when the policy or strategy was in effect. Then the essence of the difference in differences approach is to compare the outcomes before and after among the treatment group relative to the control group. Formally, the difference in differences can be modeled by an equation y subscript it equals beta subscript 0 plus beta subscript 1 times an indicator of treatment times an indicator of the post period plus beta subscript 2 times x subscript it plus u subscript it. In this equation, I is the group identifier. I equals 1 refers to the treatment group. I equals 0 refers to the control group. T is a measure of time. And post subscript T is the period after the implementation of the policy equals 1. And if in the time period, in the times before the implementation of the policy, post subscript T will be equal to 2. The coefficient of interest, the so-called DIT estimate, is beta subscript 1, which is the effect of the treatment on the treatment group relative to the control group. If you look at the equation, for the treatment group during the post-implementation period, treat subscript I will be equal to 1, and post subscript T will be equal to 1. So the product of those two terms will be 1, and so beta 1 will be identified. By contrast, for the control group, treat subscript 1 I equals 0, and for the period before the implementation of the policy, post subscript T equals 0. So for either the control group or the period for both groups prior to the implementation of the policy, the product treat times post will be 0, and beta 1 will not be identified. The key issue in a difference in differences analysis is whether the control group provides an appropriate counterfactual. And in the graphically, the way to study this is to draw the trends in the outcome, y, prior to the implementation of the effective date of the policy or strategy, to see whether the trends in the y variable, the outcome, were the same for both the treatment group and the control group prior to the effective date. And if they are, then this suggests that the control group is quite similar to the treatment group, except for the application of the treatment at the effective date. This is generally called a parallel pre-trends condition for difference in differences. In the main lecture, we discussed the difference in differences approach to estimation. So here, I will go straight to instrumental variables. An instrumental variable is an approach that can correct for simultaneity, reverse causation, limited variable, or non-classical measurement error. So this magic solution, apparently, depends on these three conditions. We must be able to find an instrumental variable that is correlated with the explanatory variable of interest, and in one direction. These are respectively the relevance condition, that the instrument is correlated with the explanatory variable, and the monotonicity condition, that relevance, that correlation be in one direction. It cannot be up and then down, or down and then up. The third condition on the explanatory variable is that it must be correlated with the outcome only through the explanatory variable. This is called the exclusion condition. There cannot be a direct link from the instrument to the outcome. Now I'll explain these in the context of a concrete example next. The example comes from a study that I carried out on supermarket cashiers and asking how the rate at which supermarket cashiers scan purchases affects their productivity in collecting payments. And we measure the productivity in collecting payments by the time. So longer time would be less productivity. Now we could think of ordinary least squares estimation. We regress the time on collecting payments on scanning speed, but there's possibly confounded. So for instance, if the queue is longer, the cashier will be working under more pressure, and because of the more pressure, she or he will scan faster and also be faster in collecting payments. So we would see a natural relationship between negative relationship between faster scanning and shorter time of payments, but not a causal relationship because it's due to some third outside omitted variable. Here's an approach that we took that seems to work. We thought of the number of packs of vegetables as a possible instrument. In Singapore supermarkets, unlike Western supermarkets, vegetables are not sold loose. They're all sold in packages of fairly standard sizes and with barcodes affixed in a regular place. So they are relatively easier to scan and so faster than, say, dealing with a box of orange juice where the cashier will have to fumble around to look for the barcode. And that's the relevance condition. So there's a direct relationship between the number of vegetable packs and the scanning speed. The more vegetable packs, the faster the scanning. And then as to the exclusion condition, there's no necessary relation between the number of vegetable packs and the scanning, the payment time. The payment time to pay for vegetables is no different than paying for orange juice. In an instrumental variables estimate, we would study three regression equations. The first is called the reduced form. It's an estimate of the outcome on the instrument. So in this case of the supermarket cashier, we would regress the payment time on the number of vegetable packs. This is the contrasted with the instrumental variable estimate, which comprises two stages. In the first stage is the estimate of the explanatory variable on the instrument. So we regress scanning speed, which is the explanatory variable that we're concerned about, on the number of vegetable packs. That's the first stage. In the second stage of the regression, which is the IV estimate, that's the estimate of the outcome on the predicted explanatory variable based on the instruments. So we regress the payment time on the scanning speed, but not the scanning speed as such, which would be the ordinary least squares regression, but the scanning speed as predicted by the number of vegetable packs. Let me review instrumental variables from another perspective, which is the potential outcome perspective. This applies when we have an explanatory variable and an instrument which are binary. That is, they're either on or off, 0 or 1. The question I have in mind is, what is the effect of training on earnings? So, to what extent people with more training earn more? We could analyze this with ordinary least squares. That is, regress earnings on training. But that might be confounded An obvious omitted variable is individual skill. Some people are inherently more capable than others. They will earn more, and they might also be people who go for training. Then we won't know if their earnings are higher because of the individual skill or because of their training. On the right-hand side, you see a photo which I took in a Singapore shopping mall. This stall is offering English lessons, a form of training that would help people perform better in service-related jobs, where they will deal with English-speaking customers or English-speaking clients. What's interesting, highlighted here in this photo, is that the instructor is highlighting that the Singapore government will subsidize the tuition fee for these English lessons up to $200. I'm now going to argue that that may be a useful instrument. The Skills Future credit, which would have paid up to $200 for that English lesson, was introduced in February 2015 in Singapore. It's available to Singapore citizens aged 25 and above. It pays $500 and additional top-ups for education and training. Now suppose that we assume that the Skills Futures credit affects individual earnings only through changes in training. We can then design a quasi-experimental study by comparing two groups of people. The control group are permanent residents. They're not eligible for the subsidy. The treatment group are Singapore citizens. They're eligible for the Skills Futures credit. If we look at each of those groups, they will be divided into three outcomes. In each of those groups, there will be one which never undergo training, another group which either does not undergo training or does undergo training, and a third group which always undergo training. The key in the study is to compare those in the control group who do not train with those in the treatment group who do train. In the language of potential outcomes, these are called compliers. The treatment group who do take the training are complying with the policy of getting the subsidy and undergoing training. The control group who don't train are complying with the policy of not getting the subsidy and not training. So that's where we see the difference in outcomes driven by the subsidy. Using the potential outcomes perspective, in this example of the training subsidy effect on earnings, the reduced form is called the intention to treat, or ITT. We compare the earnings of those eligible for the subsidy versus those not eligible. The instrumental variables estimate will generate what is called the local average treatment effect. We can do that by dividing the ITT estimate by the increase in the proportion of those who take the training. So equivalently, it's the effect on the compliers only. And if you go back to the previous slide, it's essentially comparing the two groups within the red box, the compliers in the control group versus the compliers in the treatment group. Let me conclude with two references for further reading. Both are written at a fairly elementary level and focus on this idea of econometrics for causal inference. Thank you very much.